Hello, welcome back to Control Systems lectures. In the last lecture, we presented two essential concepts that will enable us to understand the rest of the materials in our study of root locus. We explained the main problem with the feedback control system, in which the poles of the closed-loop transfer function are not easily known without factoring them, and which are also influenced by the gain of the system. Since the system's transient response and stability depend on the poles of T of S, that is the closed-loop transfer function, we can only know the system's performance if we can factor the denominator for specific values of K. Secondly, we reviewed complex numbers and their vector representation. We are now ready to define root locus and apply it. Let us use the first order system to define and explain the root locus. Consider the first order feedback control system shown in this figure. The open loop transfer function will be given as k over tau s, and the closed loop transfer function is k over tau s plus k, where k is the gain of the system and tau is the time constant. The root locus is plotted by varying the value of k from 0 to infinity. It will start from the open loop pole, and if there is an open loop 0, it will terminate at that point. Otherwise, it will terminate at infinity. In this case, the root locus will therefore start at s equals to 0 and terminate at infinity. To trace the root locus, let us take tau equals to 5, and then we vary the value of k of the characteristic equation 5s plus k equals to 0, and finding the poles, which we will then plot on the s-plane, where s is equals to minus k over 5. We can see that the root locus started at s equals to 0 and moves along the real axis to infinity. Since this is a first order system, we have one locus. The second order control systems are equally straightforward. Let us draw the root locus of the second order system shown in this figure. The open loop transfer function of the system is given by g of s of s, which is k over s plus 10. Therefore, the open loop poles are s equals to 0 and s equals to minus 10. And the open loop 0 do not exist. Therefore, the two loci will start at s equals to 0 and s equals to minus 10. And both loci will terminate at infinity. The closed loop transfer function is k over s plus 10 plus k, and the characteristic equation is therefore s squared plus 10s plus k equals to 0. You can immediately see that the poles depend on the values of k. To plot the root loci, we will vary k from 0 to 50. This could be to infinity. And for each k value, we will compute the closed loop poles, which are then tabulated in this table. The root loci will start at the open loop poles s equals to minus 10 and s equals to 0. Hence, with k equals to 0 for the closed loop transfer function, the roots are on the starting points, that is minus 10 and 0. And as k varies, the poles of the closed loop indicates the locus from 0 moving to the left of the real axis, and the locus from minus 10 moves to the right on the real axis. This is better visualized from the root locus plot itself. The root locus shows the changes in the transient response. As k varies, the poles are real and distinct for gains less than 25. Therefore, for this range of k values, the system is overdamped. At k equals to 25, we have repeated roots, which means our damping ratio is 1, and hence our system is critically damped. The system then breaks into the complex conjugate region for gains above 25, and hence the system becomes underdamped. Now, if you focus on the underdamped region, you will observe that regardless of the values of the gain, the real part of the complex conjugate remains the same. Since the settling time is inversely proportional to the real part, it means that for the second order system, the settling time will remain the same for gains above 25. Also, as we increase the gain, the damping ratio decreases and hence our percentage overshoot increases. Since the damp natural frequency is equal to the imaginary part of the pole, as the gain increases, there will be a reduction of the peak time. And finally, since the root locus never crosses into the right side of the S-plane, it means that the system is stable and will remain stable for all values of the gain. So now, so far, we have used examples of first order and second order systems to show how the root locus is plotted and to provide some insight into the information that will enable us to use it for both analysis and design of control systems. In both cases, we needed the factorized form of the denominator of the closed-loop transfer function to plot the root locus for various gains. For systems of higher gains, say 5th or 10th order, this will be near impossible. Now, I would like to provide a more general procedure for plotting the root locus for higher order systems. First, we will explore the properties of the root locus that will enable us to sketch the root locus for higher order systems without having to factor the denominator of the closed loop transfer function. Let us consider this general control system. The closed loop transfer function will be given by equation 8.4. A pole S will exist when the characteristic polynomial in the denominator becomes 0, or kg of sh of s is equals to minus 1, where minus 1 is represented in polar form as the magnitude 1 and the angle 2k plus 1 multiplied by 180 degrees, where k is a whole number, 0 plus or minus 1 plus or minus 2, and so on and so forth. Alternatively, a value of s is a closed loop pole if the length of the vector kg of sh of s is equals to 1, and the angle kg of sh of s is equals to 2k plus 1 multiplied by 180 degrees. Equation 8.5 implies that if a value of s is substituted into the function kg of sh of s, a complex number results. If the angle of the complex number is an odd multiple of 180 degrees, that value of s is a system pole for some particular value of k. And since the angle condition is satisfied, we need to satisfy the magnitude criterion. That is equation 8.6. Therefore, k is equals to 1 over the length of g of s, h of s. What we have just discovered is that a pole of the closed loop system causes the angle of kg of sh of s to be an odd multiple of 180 degrees. Also, the magnitude of the open loop transfer function must be 1, implying that the value of k is the reciprocal of the magnitude of the open loop transfer function when the pole value is substituted for s. Let us demonstrate this with the previous second order system, in which we had closed loop poles at minus 9.47 and minus 0.53 when the gain is 5. For this system, therefore, kg of s, h of s is equals to, that is the open loop transfer function, is equals to k over s plus 10. Substituting the poles at minus 9.47 for s and 5 for k yields minus 1. You can try solving for the other values of poles and their corresponding gains to confirm that you will always get open loop transfer function multiplied by the gain equals to minus 1. The angle condition, equation 8.5, is better visualized graphically. Let us apply the complex number concept we reviewed in the last lecture to the root locus of this block diagram. You can see that the open loop transfer function of this system is given by equation 8.9, and the closed loop transfer function T of S is given by equation 8.10. If point S is a closed-loop system pole for some value of gain k, then S must fulfill the condition of equation 8.6 and 8.7. These are the magnitude condition and the angle condition, respectively. Let us consider a point S equals to -2 plus J3. The angle condition will be given as the sum of the angles of the zeros represented by theta subscript 1 and theta subscript 2 minus the angles of the poles given by theta subscript 3 and theta subscript 4. This gives us a sum of 70.55 degrees, which does not satisfy the angle condition. Therefore, the point -2 plus J3 is not a closed loop pole for any gain. If we repeat the same calculations for a pole S equals to -2 plus J square root of 2 over 2, the angle will add up to 180 degrees, which means this point is on the root locus for some value of gain k. We can then calculate that value of gain using equation 8.11, which will yield k is equals to L subscript 3, L subscript 4 over L subscript 1 and L subscript 2. So if you have to compute the length of these vectors, and this will give us 0.33. This means that the point S -2 plus J square root of 2 over 2 is a point on the locus with a gain of 0.33. Let us solve an example. Given a unity feedback system that has the forward transfer function g of s equals to k s plus 2 over s squared plus 4s plus 13, do the following. A. Calculate the angle of g of s at the point -3 plus j0 by finding the algebraic sum of angles of the vectors drawn from the zeros and poles of g of s to the given point. B. Determine if the point specified in A is on the root locus. And C. If the point specified in A is on the root locus, find the gain k using the length of the vectors. The open loop transfer function is given as g of s h of s, which is equal to k over ks plus 2 over s squared plus 4s plus 13. Therefore, we have 1, 0 at -2 and 2 poles at -2 plus or minus j3. We can then draw the vectors as shown in this figure. And from the vectors, we check for the angle conditions, which is the sum of angles is equals to 180 degrees minus tan inverse -3 over -1 multiplied by tan inverse -3 over 1, which comes down to 180 degrees. Hence, the angle conditions are met. Now let's look at B. Since the angle conditions are met, it means the point -3 lies on the root locus. We can now find the gain value for this point, which gives us k is equals to 10. Please go through the example again to consolidate the concepts. Thank you for listening, and please prepare your questions so that we can discuss them during the class session.